Hi there, how's it going? Terry Brown, Mechanical Engineering here again with another engineering mechanics video solution. So let's get stuck into the problem. Alrighty, so here's the problem. We have a beam here loaded with a couple of forces and an applied couple moment on the end. And for this problem, we want to determine the X and Y components of the resultant force and specify the distance where this force acts from point O. So this is an equivalent systems problem. So usually what the easiest way to solve this problem is to find the equivalent single force and couple moment at a location. So in this case, probably point O. And then from there, work out where the equivalent single force will act. That's equivalent to the resultant force and couple at some point. Right, so that's what we're going to do in this solution. All right, so determine the resultant X and Y components at point O, and then also determine the resultant moment at that same location, and then use the moment equation to find the equivalent single force location somewhere else. Starting with the resultant force in the X direction, so we just add up all of the components of forces in the X direction, indicating that to the horizontal to the right is positive. So done that. So we've got two forces here, 500 newtons, and they're both, the directions are given by these 3-4-5 ratio triangles here. So we can make use of that to determine the components. Over here we have 4/5 times 100, so just using this 3-4-5 triangle. So we'll have a horizontal force of 400 newtons here, and then also a horizontal force of 400 newtons in the opposite direction. And our Y, some of the forces in the Y direction, so we have two forces here, so they'll be 3/5 times 500 vertically downwards, and same as this one over here. Okay, and they're in the negative direction, so that's what we have there, so minus 600 newtons. The sum of the forces in the X direction is equal to 0, right? All right, so if we draw those forces on our structure there at point 0, that's what we've got. We now need to know what the resultant couple moment at that location is as well. So you just need to say we're going to take moments about point O, and we're indicating anti-clockwise as positive. So we just want the sum of the force times distances to point O for each of our forces that are applied, plus any applied moment couple moments, and in this case we have one. All right, so MO, moment couple at point 0, we have this first force here, so 3/5 times 500, so the vertical component acting downwards at a distance of 2, so that will tend to cause a rotation around this way, right? So that's clockwise, so that's going to be negative. That's why we have the negative out the front. So get rid of that. Let's move on to our next one. So we have our force over here. Again, vertical component is 3/5 times 500. Let me just quickly draw in those components for you. Okay, so there we have the components. Again, note how I draw my components in their correct lines of action. So if you're used to drawing components out like this, over here, instead of over here, then try to get out of the habit of doing that. Okay, because in most engineering problems, we have to work out moments. Okay, so drawing your component over here, instead of where it properly acts along its line of action, can be a little bit confusing or misleading about or when you calculate the moments, right? So we're looking for the perpendicular distance, right, which is 2, right? So if we've got our force component drawn over here, right, it doesn't look like it's 2, right, if you've got the component here. Right? So draw it where it properly acts. So here we can see with this one, 3/5 times 500 times this perpendicular distance here 4, and hopefully you can see that that's going to tend to rotate around 0.0 clockwise, so that one's negative also. And then we've also got our applied couple moment at the end here. Right, so just include that as 600 Newton meters. Right, note that because it's a couple, right, it could have been drawn anywhere along here. Right, could have been drawn. We could have drawn that moment here, and it wouldn't change the solution. Okay, doesn't change the external effect on the body, and you'll see that as we do some extra calculations on this problem. Okay, so what I'm going to do is to find the reactions at the supports, do a rigid body equilibrium solution as well, to find the reactions at the supports, and do it 3 times. First for the original loading, second for the equivalent loading at 0.0 with a force and a moment, and then for the equivalent loading where we've just got a single force applied. All right, so let's get rid of that and continue on with the solution. So if we put all that into our calculator after noting that these horizontal components, their lines of action pass through 0.0, so they will have no moment effect about 0.0. Okay, so once we've done that, put that into our calculator and we get minus 2,400 Newton meters for our resultant moment. So we can put that on our diagram. All right, so now we have the equivalent resultant force and couple moment at 0.0. That's equivalent to our original loading. All right, so the next part of the problem was to find the location of just a single force. Okay, so we now want to find an equivalent single force that's the same or has the same external effect on the body as this force and this moment. If we're going to put a single force somewhere, for it to be equivalent to this force and this moment, it'll need to be out to the right somewhere. So it's got to be out there. We don't know how far, so label that with an unknown distance d. So we know that the moment that we need to get is what we got up here. We know what Ry is, we just need to get Rd. So if we rearrange that equation, divide the moment by the force, we get our distance of 4 meters. So just reiterating our solution, we got our resultant force is minus 600. So hopefully you can see that pretty obviously from up here. So the 2 horizontal forces cancel out. Vertical component here, 3/5 times 500 is 300. 300 plus 300 is 600 in the negative direction. So that's what we got. And then that needs to act at a location 4 meters from 0.0 for it to be equivalent in terms of the moments. All right, so that's the end of that part of the question. Let's move on to determining the reactions at the supports. Okay, so we're going to start with the original loading and do a rigid body equilibrium problem. So our solution plan, as usual, is to draw the free body diagram, use our equations of equilibrium, solve for the unknowns, and then check our answers. And we'll be checking our answers by doing the problem 3 different ways, using the 3 equivalent loading systems that we've just seen. Okay, so drawing the free body diagram, start with the body, add all the loads on, and then think about what forces and or moments are going to be exerted on the body by the supports. So here at the right hand end, we've got a roller support. So that's only going to have a vertical force. Then at the left hand end here, we have a pin connection. So we'll have a vertical reaction and a horizontal reaction. So now we can start to write our equations of equilibrium. So sum of the forces in the x direction equals 0. Now, as soon as I start to write an equation that says force in the x direction, I need to indicate what that is. So I put in here an indication of the x and y axes, and also an indication of what I'm taking to be positive for the moments. So for equilibrium, sum of the forces in the x direction equals 0. To the right is positive. Sum of the forces in the y direction, and then sum of the moments anti-clockwise equals 0. Okay, so there are three moment equations that we're going to use. Usually we'll start with a moment equation, because that normally enables us to find one of our unknowns straight away. So we write down some of the moments, but now we need to decide where we're going to take moments about. Okay, and usually we'll take moments about a point where at least one of our unknowns passes through. Okay, so over here at the left-hand end, we've got a location where both of our unknowns pass through here. So these two will have 0 moment about this point. So that will enable us to work out this force on the right here straight away. So let's call that point A, and then indicate on our formula here that we're taking moments about point A. Anti-clockwise is positive, all equals 0. So now we can start looking at each of our forces and all moments that are acting. So we've got our forces here. So just showing here our components again. So we've got 500. Vertical component here is 3/5 times 500. And its perpendicular distance to point A is 2. And we need to now work out whether it's positive or negative. So I think you can see that that's going to tend to rotate around this way, around point A. So that's clockwise. So therefore we put a negative sign out the front here, right? Because we've taken anti-clockwise as positive. All right, so let's move along to the next one. So we got 500, 3/5. So again, the vertical component of this force, where does it act? From point A, perpendicular distance is 4, so we can multiply by 4 there. And as it's on the same side of point A as our previous force was, that's going to cause a clockwise rotation as well, so negative for that one. Then we also have our 600 Newton meter couple that's applied, and that's going clockwise, so that's negative. And then we have our force here at our roller support. We didn't have a label yet, so we've labeled that RB, so we can put that into our equation over here. So that will be RB times 6, and tending to rotate anti-clockwise about point A, so therefore that one will be positive. Okay, so we've got everything that we need now, so we can put that equal to 0. Now, something that I've had to do here because of the way the drawing was done in the textbook. Okay, so in the textbook, it was shown that these forces act above the center line of the force, so above the center line of the beam, right? So here, our pin connection is, we assume, at the center line of the beam. So there is actually a distance between these horizontal forces and this point here, A. Now, in this case, the two forces are equal and opposite, so their moments are going to be 0 anyway, right? But if they were different values, then there would be a little moment generated here, right, about point A, due to these horizontal components. We're not given any information about the thickness or the depth of the beam, so I just have to assume that the depth of the beam is negligible, and therefore, if these horizontal forces were different values, that their moment effects about point A would be negligible. Okay, continuing on. So if we put all of this, rearrange this equation, put it into our calculator, and hopefully solve for RB and get 400 newtons. Okay, so that's the easy part. sorry, that's the more difficult part. The easy part now is doing sum of the forces. So sum of the forces in the vertical direction equals 0. So we now need to label our other forces. So over here on the left at A, I've labelled the vertical force RAY and the horizontal force RAX, because I'll need to refer to those in writing my equations here. All right, so RAY is going upwards, so that's positive. Then we've got minus 2 times 500 times 3/5. So the two vertical components here. And then we've also got RB over on the right in the positive direction, all equal to 0. So we calculated RB up here already, so we can just put that into our equation, rearrange and solve for RAY to get 200 newtons. And just to round it off, sum of the forces in the x direction equals 0. RAX will be equal to 4/5 500. So this one minus 4/5 times 500 this one, so RAX will be equal to 0. Okay, so that's solving for the unknown reactions with the original loading. Let's now do the problem again, right? Solve for our unknown reactions by using the first equivalent loading that we came up with. Okay, so instead of our two forces and a moment, we've now got just a single force and a moment acting at point O. So let's do the same thing again, use our equivalent system 1, label our locations. So we've got A and B again, we've got RB on the right as our unknown vertical reaction, and RAY and RAX as our vertical and horizontal reactions at A. So there's our free body diagram. Use our equations of equilibrium. So this time I'm going to do something a little bit different. I'm going to take moments about point B instead of point A. You could take moments about point A if you want. In fact, why don't you do that as an exercise? Right, so looking at what we've got here, so we've taken anti-clockwise as positive. So our applied couple moment here is 2,400 Newton meters clockwise, so that's negative. We've got RY times 6, okay, and that's tending to rotate about point B. So remember, we're taking moments about point B this time. So that will tend to rotate around that way, which is anti-clockwise. This term here is positive. And then RAY over here, that force is tending to rotate that direction about point B. So therefore that's clockwise. So therefore we have a negative sign out here. Okay, so hopefully this indicates to you how important it is, or why it's important that we have the letter here indicating where we're taking moments about. Right? Otherwise we've just got to guess. Right? And if you have to guess what's going on in your solution, then it's incomplete. That's all equal to 0. Do our sums, or rearrange the equation first, put our sums into our calculator, and we get RAY equals 200, which is what we got before. Okay, so now looking at some of the forces in the vertical direction equals 0. We have RAY minus RY plus RB equals 0. RA we found above, so we can just substitute that in here. Substitute from there into here, rearrange and calculate RB, which is 400, which we got before. And now to finish things off, sum of the forces in the x direction equals 0. And obviously RAX is equal to 0. All right, so that's all the same reactions that we had before. All right, so now let's look at equivalent system 2. So equivalent system 2 was just a single force, Ry equals 600 newtons, 4 meters to the right from point O. Label everything again, put on our unknown forces at our reactions, apply our equations of equilibrium. Right, so this time I'm going to go back to starting with some of the moments about point A. So we'll have 600 times 4, and hopefully you can see that that will tend to rotate around clockwise. So that's going to be negative. Put a negative in front of that one. And we also have our force out here, RBY times 6. And that's going to tend to rotate anti-clockwise. So therefore this one's going to be positive. Put that in, all equal to 0. Rearrange and solve for RBY, and we get 400 newtons. Right, same as we had before. Okay, so let's apply another equation of equilibrium. So this time I'm going to use another moment equation instead of sum of the forces, just to show that you can do that. So we have 600 times 2. So this time we have our 600 Newton force, perpendicular distance to point B. Right? So note the importance of indicating where you're taking moments about. So this distance here is 600 minus 4, gives us 2. And about point B, that's going to tend to rotate anti-clockwise. So here this is going to be positive. And then we also have now our RAY force over here times 6. And it will tend to rotate clockwise about point B. So that one's negative, all equal to 0. Rearrange and solve for RAY, and we get 200 newtons. And then, of course, sum of the forces in the x direction equals 0, so RAX equals 0. And we have the same reactions as before. So now what we've done is to find our external reactions for the 3 different loading cases that are equivalent. Okay, so hopefully now you've got a better understanding of the fact that with our equivalent loading, the external effect on the body is the same. Okay, and what we mean by the external effect is the reactions at the supports. What will change, of course, is the deflected shape and the stresses. So as we go through and start to look at calculating the stresses in a beam, loaded beam like this, the deflection that you'll get and the stresses that you'll get would be different if you loaded it in these 3 different ways. Okay, but in terms of the external effects, all 3 are the same. All right, so that's it for this problem. Hopefully that was helpful and interesting for you, and gave you a bit more of an insight into couples and moments and equilibrium and equivalent systems. All right, catch you in the next video. Bye for now.